If we eliminate the plus signs and the powers of the variables a and b in the triangular array of binomial coefficients with which we began this section, we're going to get this triangle. This is called Pascal's Triangle in honor of Blaise Pascal. We use it in his work, but certainly didn't discover it. It appeared in 1303 Chinese text, The Precious Mirror by Ku Shiche, who referred to it even then as a diagram of the old method for finding eighth and lower powers. For convenience, though, we refer to the top one in Pascal's triangle as row 0. This allows us to associate the numbers along row n with the expansion of a plus b to the n. So if you notice, we have 1s all around the top of the triangle. So we'll have 1 in row 0, a plus b in row 1. Then if you notice, we take the 1 and the 1 and we get 2. Then we take, in the next row, we take the 1 and the 2 and get 3. 1 and 3 we get 4, 3 and 3 we get 6, and so on and so forth. So really, you're adding the two numbers that get to it. Now, if we wanted to create the 6th row, we'd have add a 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And a 1. To do the 7th row, we'd have a 1. 1 plus 6 is 7. 6 plus 15 is 21. We have 35, 35, 21, 7, 1. So really, we're just adding the parts to it. This is very big. It makes things a heck of a lot easier. Because really, if you had a plus b to the 8th power, you don't want to have to do a plus b 8 times. Now, Pascal's triangle is so rich in patterns that people still write about them today. One of the simplest patterns and one that we're going to use for getting from one row to the next. So if I have to do m plus n to the 6th power, that's going to be our blue row up there. So m plus n to the 6th power. So really we'll have m to the 6th plus 6 m to the 5th n plus 15 m to the 4th n squared plus 20 m to the 3rd n to the 3rd plus 15 m squared n to the 4th plus 6 m n to the 5th plus n to the 6th. So once you get the hang of it, it's really not going to be that hard. Now, if we have to do p plus q to the 8th, what we can simply do, we can simply add another row here. So 1, 8, 28, 56, 70, 56, 28, 8, 1. So that's what we're going to have there. And I'll keep this here just for guidance. So when we create our expansion here, so I have p to the 8th plus 8p to the 7th q plus 28p to the 6th q squared plus 56p to the 5th q to the 3rd, 70p to the 4th q to the 4th, 56p to the 3rd q to the 5th, 28p squared q to the 6th, 8p q to the 7th, and then q to the 8th. So there's your expansion. Again, not super difficult, but you have to know how to do this to make it a little easier for yourself in future classes. Now the technique used in example 1 to extend Pascal's triangle depends on the following recursion formula. N choose R equals n minus 1 choose R minus 1 plus n minus 1 choose R, or equivalently n choose R equals n minus 1 choose R minus 1 plus n minus 1 choose R. So we have the two different equivalent equations there. Now here's a counting argument to explain why this works. Suppose we're choosing R objects from n objects. As we have seen, this can be done in n choose R ways. Now identify one of the n objects with a special tag. How many ways can we choose R objects if the tagged object is among them? Well, we have R minus 1 objects yet to choose from. among the n minus 1 that are untagged. So n minus 1, choose r minus 1. How many ways can we choose r objects if a tagged object is not among them? This time we must choose all r objects among the n minus 1 without tags. So that's why we have n minus 1 choose r. Since our selection of r objects must either contain a tagged object or not contain it, that's where we get the n minus 1 choose r minus 1 plus n minus 1 choose r counts all the possibilities with no overlap. Now, it's not necessary to construct Pascal's triangle to find specific binomial coefficients, since we've already found a formula for computing them. N choose r equals n factorial over r factorial times n minus r factorial. That's what we learned in section 9.1. This formula can be used to give an algebraic formula for the recursion formula above, but we will leave that as an exercise for the end of this section. Now, in example 3, find the coefficient of the given term in the binomial expansion. Well, we want to find the x to the 10th term in x plus 2 to the 15th. So really, what we're going to be doing here, we're going to be doing 15 choose 10, x to the 10th, and 2 to the 5th. One thing that we need to remember, the 10 and the 5 have to add up to 15. Now, when we do 15 choose 10, this will really be 15 factorial over 10 factorial times 5 factorial. So in your calculator, 15 factorial divided by 10 factorial, 5 factorial. That will give us 3003. Also, what we're going to have to do then, so this will be 3003 times 2 to the 5th, which is 32, times x to the 10th. So really what this is going to be then, when we take 3003 times 32, we get 96,096. X to the 10th. There's our x to the 10th term. Now when we do x to the 7th term, we're going to do 11 choose 7 times x to the 7th times negative 3 to the 4th power. Well, 11 choose 7 is really 330 times x to the 7th, and negative 3 to the 4th would be 81. So 330 times 81, 26,730.